Hello everyone, this is Mr. Underkoffler, and today we're going to be looking at the PSSA Big Ideas Geometry Topics. And this is 2 pages worth of review on geometry topics that we've gone over at the 7th grade math pre-algebra level. All right, we're going to start with a quick review on some vocabulary and symbolism. Anytime you hear me talk about the word congruent, congruent means having the same measure or equal measure. Per se. The symbol for congruence is an equal sign with a little wave on top. The symbol for an angle looks like an angle, which is quite convenient. And if you ever want to talk about the measure of an angle, you will put a little m to the left of the angle symbol, and then to the right of the angle symbol could be whatever the name of the angle is, which could be written with a number. If we're talking about angles 1, 2, 3, and 4, it can be written with a capital letter if we're naming an angle after its vertex. Different ways of doing that. And then a real quick review: acute angles, obtuse angles, right angles, straight angles. This is probably stuff you learn in 5th and 6th grade math. Right angles, you will always see the little square in the corner. I shouldn't say always, but if you ever see the square in the corner, that means a right angle, 90 degrees. Straight angles do look like straight lines, and they measure 180 degrees. Now, specifically at the 7th grade level, we learned about things called vertical angles, complementary angles, supplementary angles. So let's quickly go over these. Vertical angles are a pair of angles that are opposite of each other when 2 lines intersect. So you can see here we have angles opposite of each other from 2 intersecting lines, and those 2 angles there are vertical angles. You can see they are congruent to each other, which vertical angles always will be. Now, they don't have to be left and right of each other. They could be above and below each other from 2 intersecting lines. But again, they're angles opposite of each other, not right next to each other. It's not like the angle here and the 102-degree angle. No, 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 no. They are angles opposite of each other where they do share a common vertex in between, but they do not share a common side. When I say a common side, I mean like a ray going here. You can see the other 40-degree angle on the right does not have that ray. So that's what I mean by opposite of each other. Complementary angles are a pair of angles whose sum is 90 degrees. Now, often you can find them when a right angle is shown. Now, this is a kind of creative example. The right angle was drawn on the left. It was not drawn on the right, but since this is a straight angle here, then we could also conclude that another right angle could be drawn over here where the 40 and 50 together would create. And so that's a way of seeing that you have a pair of complementary angles. But they don't have to be 2 angles that are right next to each other. They can be 2 completely separate angles at different locations. If the sum of those angles is 90 degrees, then they are a pair of complementary angles. Supplementary angles are a pair of angles whose sum is 180 degrees. And again, they don't even have to be next to each other. If their measures add up to be 180, they are a pair of supplementary angles. Now, an easy way to locate them would be 2 angles that together form a straight angle. And you can see here, if I have a 130-degree angle and a 50-degree angle, they together form a 180-degree straight angle, and they are a pair of supplementary angles. But again, even though a lot of the drawings we've seen this year were 2 angles that together formed a straight angle, that doesn't always have to be the case. They could be 2 angles that are completely separate, but their measures would add up to be 180 degrees. Now, let's talk about angles that are formed when 2 parallel lines are cut by a transversal. And when we say cut by a transversal, we mean they're intersected by another line. And so the 2 parallel lines that are intersected by this diagonal line on the drawing that I keep showing here on the bottom half of the page, that diagonal line is the transversal, just to kind of catch you up here. Now, many different angles are formed from this situation. Let's first talk about corresponding angles. They are a pair of angles in matching positions. Now, why should we care? Because they're congruent to each other. So this angle here on the top right-hand corner is in a matching position of the angle down here, also in the top right-hand corner, but in the bottom part of the picture. So they're in matching positions, and as you can see, they are congruent, both 115 degrees. Likewise, here I have an angle in the bottom right-hand corner. Here I have another angle in the matching position, bottom right-hand corner, but of the upper part of this drawing. They are matching positions. They are a pair of corresponding angles. And as you can see, they have the same measure. Now, I only gave you 2 examples here. I could have also talked about the angle up here in the top left-hand corner and how it matches the angle in this position. So they're corresponding angles. I could have talked about the bottom left-hand corner and how it matches with the angle in the same position up here. So 4 different pairs of corresponding angles from this diagram. All right, let me get rid of all my highlighting here because this is getting rather messy. Let's also talk about how in this diagram you can also find many pairs of vertical angles, actually 4 different pairs of vertical angles. You can also find some pairs of supplementary angles. So vertical angles, remember, are formed when 2 lines intersect, and the vertical angles would be angles that are opposite of each other. So here we have 2 intersecting lines at the top, and you can see these angles that are opposite of each other are congruent. They are a pair of vertical angles. Supplementary angles are 2 angles that add up to be 180. Easy way to find it on this kind of drawing is any straight line and any 2 angles that together would form that straight line, they would add up to be 180 because the straight line itself is a straight angle which measures 180 degrees. And anytime you have a pair of angles whose measures add up to equal 180 degrees, that pair of angles would be supplementary angles. So that's one example. And we could also find them going diagonal this way. The angle up here and the angle here together would be 180 degrees. So many different pairs of supplementary angles in this diagram. And the other kinds of angles we need to talk about that also show up when you have 2 parallel lines intersected by a transversal is alternate interior angles and alternate exterior angles. Alternate interior angles are a pair of angles that are inside. See, the word interior means inside. And when I say inside, I mean between the parallel lines, but are on opposite sides of the transversal. So you can see here, this angle here is between the parallel lines, and this angle here is also between the parallel lines, but they are on opposite sides of the transversal, and they are congruent to each other. They are a pair of alternate interior angles. Here's another pair. Again, they're both between the parallel lines, but they are on opposite sides of the transversal. And I want to clarify, I don't mean like the angle of 65 degrees here on top and the one next to it. So they're not adjacent to each other. And maybe I should have put that in the definition here. Alternate interior angles are not going to be side by side. Okay? Not going to be side by side, and they're going to be on opposite sides of the transversal. Both between the parallel lines to be alternate interior angles. Now, if they're outside of the parallel lines, and they happen to be on opposite sides of the transversal, then they're going to be what we call alternate exterior angles. So you'll see here we have a 65-degree angle above the parallel line, and then way down here we have 65 degrees below the parallel line, and they're on opposite sides of the transversal. The one here is on the top left, the other one's here on the bottom right. They are a pair of alternate exterior angles, and you'll notice they're congruent. The other pair would be the top right-hand corner and then the bottom left-hand corner. They are the other pair of alternate exterior angles, and you can see they're both the same measure. They're both congruent to each other. All right, now that I reviewed all those different types of angles, let's do 2 practice problems dealing with types of angles. So please find a separate sheet of paper. You do not have to copy down the drawing if you don't want to, but read this problem to yourself and then figure out which equation is correct. Hit pause on the video, then hit play after you figured out which one is correct. All right, let's go ahead and see how you did. Now, Are these angles congruent to each other? Well, let's see. We have this angle here, which is in the top left-hand corner. If there was an angle here, they would be corresponding angles, and they would be congruent. But that's not where the x plus 40 is located. Okay. Well, also, the angle in the top left-hand corner is congruent to the angle in the bottom right-hand corner because they would be alternate exterior angles, but that's not where x plus 40 is. The angle here is congruent to the 2x plus 20 because they're vertical angles, but that's not where x plus 40 is located. In fact, the x plus 40 would be congruent to this angle up here. They would be a pair of corresponding angles. Well, I'm pretty much proving to you that the 2x plus 20 is not congruent to the x plus 40. And let me show you something else. The 2x plus 20 appears to be an obtuse angle, whereas the x plus 40 appears to be an acute angle. But they do appear to be supplementary angles. Do you see how I'm showing you this? How the two angles together would form a straight angle, which would measure 180 degrees. So I need to have an equation that shows me that 2x plus 20 plus x plus 40 would equal 180 degrees. And it just so happens that that is choice D. Choice A would be if they were congruent, and they are not. I already explained that. Choice B is ridiculous, trying to tell you that 2 times the x plus 40 would equal 2x plus 20. We have no proof that you could take 2 times the smaller angle to get the bigger angle. Choice C is if they were complementary angles, but we have no evidence of any right angles in this diagram. So choice C makes no sense. It is choice D. All right. This one's a little bit more interesting. We have 2 intersecting lines to the parallel lines of M and N. So we have 2 transversals. Makes this a little bit more interesting. Hit pause on the video. Figure this out on your own to get the value of x. Then hit play when you're ready to see how you did. Okay. How in the world are we going to do this? Well, it just so happens that the 72-degree angle is an alternate interior angle with this angle up here that I'm highlighting in yellow. And so that means the angle up there that I highlighted in yellow would also be 72 degrees. Well, how does that help me? Well, because the 48-degree angle and the x-degree angle and the 72-degree angle, those 3 angles together would form a straight angle. And so what I can do is I can add the 48-degree angle plus the 72-degree angle and then subtract that away from 180 degrees to get the value of x. So 72 plus 48 gives me 120. If I subtract that from 180, then I will get 60 degrees. Now, there is another way you could have done this problem. You could have realized that the 48-degree angle is an alternate interior angle with this angle in the corner of this triangle that's formed. And so what that means is that that angle is also 48 degrees. Do you remember that the 3 angles of a triangle add up to be 180 degrees? In fact, I had that on the second page of this Geometry Topics Big Ideas review paper. So again, that's another way you could have realized that you would add the 48 plus the 72 and then subtract that away from 180 degrees because 3 angles of a triangle add up to be 180 degrees. And that's going to give you, once again, 60 degrees, which we can all see is choice C. All right, let's go back to the bottom of the first page of the Geometry Topics PSSA Big Ideas paper. very bottom of the first page, is a reminder on what scale is. Scale is the ratio of a given length in a drawing, or possibly in a model, to the length of the actual real-life object. For example, if you're given a scale where it says 1 inch equals 4.5 feet, what that means is every 1 inch on the drawing, or possibly on the model, would represent 4.5 feet in actual real life. Scale is used a lot, especially when you have scale drawings or models that are created to scale that represent an actual real life object. And so scale is a very important ratio which can often pop up on some geometry problems. Keep that in mind for some future problems coming up today. All right, on the second page, or the back side, if you printed this on the front and back, of the PSSA Big Ideas Geometry Topics paper are some properties of triangles. Now, the first one here, I already reviewed with you on the other practice problem that we were looking at. The sum of the angles of a triangle, the sum of all three angles of the triangle will always equal 180 degrees. But that's not going to be how the sides of a triangle work. The sides of a triangle have nothing to do with degrees. The property that is true for sides of a triangle actually has its own name, and that is called the triangle inequality theorem, which says the sum of the lengths of any two sides that you pick from a triangle, the sum of those two lengths must be greater than the length of the other side, the third side. Now, there are some very specific special types of triangles that we should quickly review. In acute triangle, all three angles are acute. An obtuse triangle will have only one obtuse angle. In this example, I made it a 90-degree angle. Notice the other two angles are not obtuse. The other two angles are less than 90 degrees. They're acute angles. A right triangle will have one right angle, as you can see here from this square. And then the other two angles will be acute. They will be less than 90 degrees. By the way, those other two angles will be complementary angles because they will add together themselves. Those two angles add up to be 90 degrees. A scalene triangle, no sides are congruent, no angles are congruent. Now, I would highly advise that you star the isosceles triangle on your page. Why? I am telling you, isosceles is a very popular type of triangle that just seems to pop up in a lot of different math problems that I've noticed that seem to show up on standardized tests. So, not that I can guarantee it's going to show up. There's no way I could guarantee because I don't know what the PSSA is going to actually have on it. But I do know isosceles triangle does seem to be popular in a lot of math textbooks. So, what is an isosceles triangle? It is a triangle that has at least two congruent sides and also at least two congruent angles. Now, both of those things will be true. So if you see two congruent angles, then you can conclude that the two sides that share those two angles would also be congruent to each other. Or you could do it the other way. If you have two sides that are congruent, then the two angles that are coming off of those two sides would also be congruent to each other. An equilateral triangle, all three sides are congruent, all three angles are congruent. All right, let's look at a practice problem that deals with, oh look, scale, but also a triangle. A scale drawing of a triangle that will be used on a banner is shown below. What is the perimeter in feet of the actual triangle used on the banner? Now, if you don't even remember what perimeter is, I do have it at the very, very bottom of the geometry topic second page. Perimeter is the distance around a two-dimensional shape. So, with that in mind, hit pause in the video, do this on your own, then hit play when you're ready to see how you did. All right, let's see how you did. First of all, there is a scale. It says that every 1 inch equals 1.5 feet. So what we're going to need to do is we're going to need to convert the inches to the amount of feet that they would correspond to in real life. But before I do that, I want to point out that the left side is not given to you. Are we just supposed to guess what it is? No. Notice how this angle and this angle are represented with the exact same variable, but the angle on top is a different variable. What they're trying to tell you is those two angles in the bottom left-hand corner and the bottom right-hand corner are congruent, which means you have an isosceles triangle, which means the side on the right that shares that one angle is congruent to the side on the left that also shares the y-degree angle, which means the side on the left is also 5 inches in measurement. So this is an isosceles triangle, and I knew that because of the two angles that were both congruent, both called y degrees. Now, we need to use the scale. We're going to take 5 times 1.5 inches and 6 times 1.5 inches. Now, you can use your calculator, and I'll be honest with you, I would use 1.5 in my calculator because that's so much quicker to punch in. So that's going to give you 7.5 or 7.5, and then 9 for the 6-inch long drawing. And I would actually replace these measurements here. So I would, if I were you, I would kind of cross out the old measurements and I would replace it with the new measurements. So the 5 inches are now 7.5 feet in real life, and the 6 inches are 9 feet in real life. So those are the numbers that I'm going to want to use. And to get the perimeter, all I need to do is add the 3 side measures together. So 7.5 plus 7.5 plus 9 will equal 24 feet. And that is the answer, choice B, to this problem. Now, I want to give you a little bit of a friendly warning here when it comes to your guided notes with scale. And this message is not on, did I say guided notes? This is not guided notes. This is PSSA Big Ideas paper. This message is not on your paper. So just look at my screen here. Make sure that you convert using scale before using formulas, such as area formulas. Because if you find the area first and then try to convert it using the scale, it's not going to work. Now, why not? Because scale, for example, like we were looking at, will show you the number of inches going to something else, like the number of feet. Well, why would this mess up with area? Area is never just inches or just feet. Area is always square units, such as square inches or square feet. And I got news for you. Inches is not the same as square inches. Feet are not the same as square feet. This is why when you have scale, you need to convert the measurements on the shape using the scale before you use the actual area formula. Whether it's the area of a circle or the area of a parallelogram or the area formula for a trapezoid or a triangle, before you use those actual area formulas, you will have to convert the measurements, whether it's base and height or radius of a circle or whatever it might be, for whatever shape you're dealing with. You're going to have to convert those measurements using the scale before you actually use the area formula. If you try to find the area first and then convert it, it will not work, because then you won't have just inches or feet. You would have square inches, which not the same as regular inches, and the scale no longer will work. So that's a helpful tip I need you to remember. All right, let's move on the Big Ideas paper. Cross sections. A cross section is the two-dimensional shape that results from slicing a three-dimensional figure. Let me say that again. A cross section is the two-dimensional shape. That means flat shape that results from slicing a three-dimensional figure. Now, when a 3D figure is sliced parallel to its base, the cross-section is going to be the same type of shape as the base was, but not necessarily the same side or same size. Now, the examples I've given you here in your paper are examples of cross-sections of a square pyramid. Now, when I say square pyramid, I mean the base is a square. So if I do a horizontal slice parallel to the base, then it's going to give me the same shape as the base. Remember how I said it was a square pyramid? That means there's a square base. So if I slice it parallel to that square base, I am going to get a cross-section being a square. Now, it'll be a smaller square than what I have on the base, but it's still going to be a square if it's parallel to the base for the slice. Now, if I do a vertical slice through the vertex at the very top of the pyramid, and it's therefore perpendicular to the base, then the cross-section will kind of like be the side view of the square pyramid, which would be a triangle. And so that's something you have to realize. Vertical slices that are perpendicular to the base have nothing to do with the base. The base was a square, but yet the vertical slice here through the vertex was a triangle. Now, I do want to point out, and this is not on your paper, if I do a vertical slice perpendicular to the base, but not going through the vertex, say it was a little bit more to the right, then as you can see here, it would not make a triangle at all if it doesn't go through the vertex at the top of the pyramid. In fact, instead, it would make a trapezoid. So keep in mind, if it doesn't go through the vertex of the pyramid, then the vertical slice could be something very different. In this case, a trapezoid. Now, angled slices to me are the trickiest of all slices to figure out the cross-section. If I do an angled slice like you see here on the square pyramid, then it's kind of like taking the square but shifting the left side up, which makes the side on the far left much shorter than what it is on the right. And so that's no longer going to be a square. Instead, it's going to actually be a trapezoid. So angled slices kind of take the shape of the base, but kind of stretch it, and that can definitely change it from what the shape of the base would be. So it's still four sides, like the base was, but it's no longer a square. It's now going to be a trapezoid. All right, with that in mind, let's do a practice problem. Barb has a jewelry box in the shape of a rectangular pyramid. So it's not a square pyramid like I was showing you on the PSSA Big Ideas paper. It is a rectangular pyramid. The top opens at a cross-section parallel to the base. What is the shape of the opening of the jewelry box? Hit pause on the video, figure out which is the answer, then hit play when you're ready to see how you did. All right, you probably didn't even have to hit pause because this doesn't really take any work. If it's parallel to the base, then it's going to be the same kind of shape as the base. And if it's a rectangular pyramid, then that means this base down here is actually a rectangle. I mean, it kind of looks like what I had on the previous problems, but we're going to say it's not a square base, it's a rectangular base because the problem told me it was a rectangular pyramid. So if it's parallel to the base, then it's going to be the same kind of shape as the base, which would be a rectangle. All right, at the bottom of the PSSA Big Ideas page, I have a review on the big ideas of area, perimeter, circumference, volume, and surface area. So, area is the space inside of a two-dimensional shape. Now, it is specifically measured by 1x1 squares. Perimeter is not the inside of a shape. Instead, it's the distance going around a two-dimensional shape. Circumference is the distance around a circle specifically. So perimeter, I should have clarified, is really the distance around a two-dimensional polygon, such as triangles, trapezoids, rectangles, pentagons, and so on. Circumference is always the distance around a circle. Volume is the space inside of a 3D figure. So that's not going to be measured with squares. That's going to be measured by 1x1x1 cubes. Surface area is area, but it's the sum of the areas of all the faces that make up a 3D figure. Now, you heard me say area is measured by 1x1 squares, and volume is measured by 1 by 1 by 1 cubes. This is why area and surface area are measured in square units, such as square feet, which are always shown with a little 2 in the top right-hand corner of that unit of measure, to be like the idea of saying squared. That's another way of saying second power. So that's why that's the symbolism for square feet. Volume is measured in cubic units, such as cubic feet, which would be a tiny little 3 in the top right-hand corner of the feet, because third power, another way of saying that, is cubed. So that's why we use the third power to represent cubic feet. Now, a couple other reminders. Radius and diameter of a circle. The radius of a circle goes from the center to an edge only halfway across. It is that line segment. The diameter is the line segment that goes the whole way across the circle through the center. Now, other things I want to talk about, and you will actually see this on your formula sheet. The base and height of a shape are always going to be perpendicular to each other, which means they're going to touch at a right angle. That is true for the triangle, for the trapezoid, and also for the parallelogram. Now, specifically, let's talk about the trapezoid. The trapezoid's bases, which on your formula sheet are called B1 and B2, they are always going to be the two sides that are parallel to each other. So base and height are always perpendicular, meaning they touch at a right angle. Bases of a trapezoid, B1 and B2, are always going to be the two sides that are parallel to each other. Okay, so let's do a practice problem. And this one is talking about the diameter of Jacob's circular tabletop is 6 feet. What is the area in square feet of Jacob's tabletop? Now you're gonna have to go to your formula sheet in order to be able to figure out this problem. So hit pause on the video, then hit play when you're ready to see how you did. All right, did you go to your formula sheet and find the area formula of a circle? Not the circumference formula, because this problem specifically wanted to know the area. So that's capital A. Now, the area formula has R, which is radius. This problem did not give me radius. This problem gave me the diameter. So diameter is not the same as radius. But if you looked here at this drawing, you probably saw, since the radius only goes half the way across, but the diameter goes the whole way across, you could cut the diameter in half and you will get the radius. So if the diameter is 6, then the radius will be 3. And that's the number you're going to substitute into this formula for the radius being taken to the second power. 3 to the second power is not 6. So if you thought radius to the second power is the same as diameter, it is not. 3 to the second power is 9. That's going to give you 9 times pi. Now notice, these answers were given in terms of pi, so you didn't even have to use your pi key in your calculator. All you really had to do was take the radius of the second power and then realize that would be taken times pi to get your area. So that's 9 times pi, which is choice B. All right, a circular lampshade with a diameter of 14 inches has a length of wire that goes around it exactly 1 time. How many inches of wire are needed to go around the lampshade exactly 1 time? All right, try this again using your formula sheet to help you. Hit pause on the video, then hit play when you're ready to see how you did. Okay, you went to your formula sheet and you had to decide which formula makes sense for this situation. Since we are talking about a wire that goes around the circle, that's the meaning of circumference. Remember how I told you circumference is the distance around a circle, whereas area is the space inside of the circle. We don't want the space inside of the circle here. We want a wire that goes around the circle. That's why we need to use the circumference formula. Now, the circumference formula, as you already saw from your formula sheet, was C equals 2 times pi times R. There is an alternate version of the circumference formula that is not on your formula sheet. and it doesn't need the 2 because it uses diameter. See, you might understand that 2 radiuses would be the exact same thing as 1 diameter. So if you want to use this alternate formula that uses diameter and doesn't use a 2, you could. It's just not going to be found on your PSSA formula sheet, which is why most kids probably wouldn't use it, to be quite honest with you. So what is the radius if you're going to use 2 pi r? They don't give it to you. They give you the diameter is 14 feet. So if the diameter is 14 feet, then the radius is 7 feet. So 2 times pi times 7, that's going to be 2 times 7 is 14. So you would get 14 times pi as your circumference, which would be choice B. Now, if you would use pi times diameter, you of course get the exact same thing. So there's your proof that pi times diameter would do the exact same job as 2 times pi times radius. Now that doesn't work for area, but for circumference, this does work. All right, the very last problem I want to do on geometry topics is right here. So read this problem to yourself, figure out what formula you're going to use, and do the work, figure out the answer, then, so hit pause and do all that, and then hit play when you're ready to see how you did. All right, so we're talking about here a rectangular prism, as you can see in the very first sentence. So when you go to your formula sheet, you're going to find a rectangular prism and a polygonal prism. Now, polygonal prisms technically could include rectangular prisms, but you might as well just use the rectangular prisms formulas, which you can find right here. If you're given a triangular prism, then you would use the polygonal prism. Or a trapezoidal prism, you would use the polygonal prism. But for rectangular prism, we're going to use its own unique volume or surface area formulas. The question is, which one are you going to use here? Are you going to use the volume, or are you going to use the surface area? Well, if you paid attention to what I taught you on the bottom of the PSSA's Big Ideas Geometry Topics second page, you're going to see that volume is measured in cubic units, such as cubic feet. Well, what did this problem talk about? It talked about cubic yards. That must be the volume. It must be. Surface area would not be in cubic yards. Surface area would be in square yards. So you actually need to remember that area is square yards or square feet. Volume would be cubic yards or cubic feet. These are big ideas you have to understand. So this is why we're going to use the volume formula. Length times width times height, which is 50 times 1.5 times 0.25. And that's going to give you 18.75 cubic yards, which was choice A. And that concludes the video that reviews the big idea topics that deal with geometry at the 7th grade level for the PSSAs. Thank you for watching. We'll see you next time.